Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's use triple integrals and cylindrical coordinates to find the volume enclosed between a cylinder and a cone. In this example, the cone is defined by the Cartesian equation where z is equal to the square root of x squared plus y squared. The apex of the cone is where z equals 0 and on the xy plane. The cylinder is defined by the Cartesian equation x squared plus y squared is equal to 4 and is bounded by the xy plane where z equals 0 and the plane where z equals 8. Let's take a look at the structure in 3D form using a graphing tool. So this is the cone in isolation, the apex of which is above the xy plane. And this is the cylinder. As you can see, it's between the xy plane and the plane where z is equal to 8. And if I put the two together, we get this structure. And if we limit the structure to where the two intersect, we get this, which looks like a rocket on one of the Apollo missions after separation. We want to find the volume within this structure. Our first step in this process is to convert the Cartesian equations of both the cone and the cylinder into cylindrical coordinates. So beginning with the cone, where the Cartesian equation is z equals the square root of x squared plus y squared, we want to convert x, y and z to r, theta and z. And to do this, we're going to substitute our cos theta for x, our sine theta for y, and z will remain the same. So z will equal z. And if we make the substitution, we have z equals the square root of r squared into the bracket of cos squared theta plus sine squared theta. And using the trig identity where cos squared theta plus sine squared theta is equal to 1, we get z is equal to the square root of r squared. And taking the positive square root, we get z is equal to r. So now we need to do the same for the cylinder. The Cartesian equation for the cylinder is x squared plus y squared is equal to 4. And after making the substitution, we get r squared into the bracket of cos squared theta plus sine squared theta is equal to 4. And using the trig substitution where cos squared theta plus sine squared theta is equal to 1, we have r squared is equal to 4. And taking the positive square root of both sides of the equation, we get r is equal to 2. To find the enclosed volume between the structures, we need to integrate over the region which we'll call E, and some infinitesimally small pieces of volume shown here as dv. We need to unpack this and define our region using cylindrical coordinates. This will give us our limits of integration for r, theta and z, and then look at what dv equates to in this context. So let's start with the limits of integration along the z-axis. To help with this, let's limit our structure to show the region of intersection. To find the limits of integration for z, the best way to think about this is that we are summing infinitesimally small pieces of volume along the z-axis between a function that defines the upper bound and one that defines the lower bound. So as we can see from this diagram, the structure has a cylinder as the upper section and a cone as the lower section, which helps us define the limits of integration. The lower limit of integration for z is therefore the function of the cone where z equals r. And the upper limit of integration is the upper plane of the cylinder, so where z equals 8. If you remember when we looked at volumes using polar coordinates, we multiplied by a height component, which was the difference between the upper function and the lower function. Well, this is essentially the same, except we are now using an integral to do this. Moving on to the limits of integration for r, if we look down from the z-axis, we see that a circle centered at 0 is cast on the xy plane. The upper and lower limits of integration for r will be along the radius of this circle, where we'll sum infinitesimally small pieces of volume. The upper bound of r is the radius of the circle, and is where the cylinder interfaces with the cone. As the radius of the cylinder is always constant, we can therefore conclude that r is equal to 2 at the interface and forms the upper limit of integration. As r begins at the origin of the circle, so where r equals 0, this forms the lower limit of integration. And to find the limits of integration for theta, we need to look at the coverage of r as it rotates counterclockwise around the circle. As we can see, r goes full circle and therefore rotates the full 2 pi or 360 degrees. So the lower limit of integration of theta, where theta begins, is at 0, and the upper limit of integration is where theta finishes, and in this case it's 2 pi radians. We've defined our region using the limits of integration. Let's now unpack what we're integrating. So in our case it's dv. So dv represents infinitesimally small pieces of volume. We're using triple integrals to sum each of these to get the total volume. Let's look at the dimensions of one of these. If we look at the green shaded region, this represents an infinitesimally small piece of volume dv. We can think of this as a tiny rectangular box where the volume is given by the height multiplied by the width multiplied by the length. So let's apply this to the green shaded region. We can see that the height is along the z-axis, and it's an infinitesimally small piece of z represented by dz. The width of the box lies along the radial distance r and is an infinitesimally small piece of r represented by dr. And the length lies along the arc of the circle and is infinitesimally small. Now the arc length of a circle is given by the radius multiplied by the central angle theta. In this case, theta is infinitesimally small, represented by d theta. If we now put all these infinitesimally small dimensions together, we see that the volume dv is given by dz rdr d theta, and we sum all these pieces of volume using our triple integrals to get the total volume. So we now have our triple integral where we are integrating dz rdr d theta. So let's begin the evaluation process, starting with the inner integral. We want to integrate from z equals r to z equals 8 dz. And using the power rule to evaluate the integral, we get z. Plugging in the upper and lower limits of integration, we have 8 minus r. And for the middle integral, we want to integrate from r equals 0 to r equals 2, r into the bracket of 8 minus r dr. And using the power rule to evaluate this integral, we get 4r squared minus r cubed divided by 3. And plugging in the limits of integration for this, we have 16 minus 8 divided by 3. And plugging in the lower limit of 0 yields 0. So we get 40 divided by 3. And for the outer integral, we want to integrate from theta equals 0 to theta equals 2 pi, 40 divided by 3 d theta. And using the power rule to evaluate this, we get 40 divided by 3 theta. And plugging in the limits of integration, we get 80 pi divided by 3. And this is the volume enclosed between our cylinder and our cone.